Hello everyone, I'm Camilla Foggia. I have a degree in natural science and I'm currently finishing my master degree thesis in ecobiology at La Sapienza University in Rome. Let me show you my work about coastal vulnerability in Mozambique. Mangrove forests are among the most productive ecosystems on Earth. They are globally recognized as highly carbon-rich tropical ecosystems that provide a number of critical economic and ecological services to surrounding coastal populations. However, the global area of mangrove forests has declined by 30 to 50% over the past half-century, with a loss rate 3 to 4 times greater than that of terrestrial ecosystems, due to human activities such as coastal development, aquaculture expansion, and overexploitation. Mangroves stabilize shorelines, reduce erosion, promote the growth and maintenance of animal biodiversity, um, by providing breeding and feeding sites for many species, and protect coastal communities from the impact of climate change. Moreover, these complex ecosystems sequester carbon at up to 4 times the rate of terrestrial forests, playing a key role in carbon storage and making them crucial resources for offsetting greenhouse gas emissions and meeting global warming containment goals. Consequently, the degradation and disappearance of these coastal shields would render the coastal areas more vulnerable to the effect of climate change and would release the significant amount of carbon stored in these ecosystems, returning it to the atmosphere and further contribute to climate change. In addition, mangrove complex and dense aerial net-like root systems dissipate wave energy and impede the flow of water. The GMA, the Global Mangroves Alliance, estimated that mangroves prevent more than $65 billion in property damage and reduce the risk of flooding for about 15 million people each year. Overall, the total areas of mangroves has been estimated at more than 147,000 square kilometers in 2020, and more than 11,000 square kilometers of mangroves have been lost since 1996, and of these, about 80,000 square kilometers are considerable by GMA to be restorable. The GMA's main goal is to restore 50% of them by 2030. As we have said, mangroves play a crucial role in protecting coastal areas from erosion and flooding, providing an important natural barrier against storms and contributing to the resilience of coastal communities. So, faced with an intensification of human activities and climate change, coastal communities need to better understand how modification of the biological and physical environment, such as direct or indirect removal of natural habitats for coastal development, can affect their exposure to storm-induced erosion and flooding. Coastal regions, which are constantly subject to the action of ocean waves and storms, naturally experience erosion and inundation over various temporal and spatial scales. However, the coastal erosion and inundation pose a threat to human population, especially in a context of climate change and increasing coastal population. Moreover, this increasing in anthropogenic pressure can lead to the loss and degradation of coastal ecosystems and their ability to provide protection for humans during storms. Thus, it is important to understand the role of various biological and geophysical factors in increasing or decreasing the threats of coastal erosion and inundation in order to better understand for future development. In particular, it is important to know how natural habitats can mitigate the forces responsible for coastal erosion and inundation, so that management action might best preserve the protective services provided by coastal ecosystems. The goals of my work are multiple. First of all, to analyze the coastal vulnerability on Mozambique coast. Through a coastal vulnerability model that allows us to examine various environmental factors that influence the stability and security of coastal areas. Second one is to provide an easy to understand tool for different stakeholders. This is because it is essential that the information collected is accessible and useful for all stakeholders, from local authorities to non-governmental organizations to communities themselves. Only through shared understanding we can implement effective strategies. Third is to identify areas of highest priority for management intervention. Using model outputs, it's possible to identify areas of highest priorities highest risk of flooding and erosion, which require urgent intervention. This allows resources and efforts to be focused where the impact will be greatest, thus ensuring more efficient and effective management. Fourth, promoting adaptive management of mangroves. My research aims to develop a basis for management activities of mangroves. This includes not only protection of existing habitats, but also the rehabilitation of degraded areas in order to restore the valuable ecosystem service. As we have said, the study area is the coast of Mozambique, that is located in the southeast coast of Africa. And this country is divided into 11 provinces, but for this work we considered just the coastal provinces that are Cabo Delgado, Nampula, Zambezia, Sofala, Inhambane, Gaza, Maputo, and Maputo City. Among the East African countries, Mozambique has the largest coastal and mangrove forest area. It is about 3,000 square kilometers, but obviously it is subject to global climate risks. The GMA reports that the extent of mangroves in Mozambique was reduced by 159 square kilometers between 1996 and 2020. Um, Coastal regions of Mozambique are particularly affected by natural phenomena such as cyclones and floods. For example, in March 2019, the central region of Mozambique, the Sofala province and the surrounding areas, was hit by the devastating Category 4 tropical cyclone Idai. And a few days later, the northern province of Nampula and Cabo Delgado were in turn hit by Cyclone Kenneth. These catastrophic events brought torrential rains, flooding, and high wind speed, causing massive destruction of coastal regions, with the very negative impacts on vegetation and reinforcing the urgency of management actions. The methodology I used to do a vulnerability assessment of Mozambique coastline was that of INVEST, specifically the coastal vulnerability model that produced a qualitative estimate of exposure to storm-induced erosion and flooding in terms of vulnerability index, which differentiates areas with relative high or low exposure to erosion and inundation during storms. Model outputs are a geospatial dataset with a spatial resolution defined by the modeler and can be overlaid with other spatial information for users to perform further analysis and as they see fit. By coupling these results with the global population information, the model can show areas along a given coastline where humans are most vulnerable to storm waves and surge. Outputs can be used to better understand the relative contribution of different model variables to coastal exposure and align the protective services offered by natural habitats to coastal population. This information can help coastal managers, planners, and other stakeholders to identify regions of greater risk to coastal hazard, which can in turn better understand, better inform development strategy and permitting. By aligning the relative role of natural habitats at reducing exposure and showing the areas where coastal populations are threatened, the model can be used to investigate how some management action or land use change can affect the exposure of human population and erosion to erosion and inundation. The exposure index represents the relative exposure of different coastline segments to erosion and inundation caused by storms within the region of interest. The index is calculated by assigning a value from 1 to 5 for each point on the coast at a distance defined by the modeler, and in this case is 100 meters, and for each point for different bio-geophysical variables such as relief, natural habitats, wind, wave exposure, and surge potential depth contour. The model computes the coastal exposure index by combining the ranks of these variables at each shoreline point. And the rank vary from very low exposure, rank 1, so very high protection, to very high exposure, rank 5, that mean very low protection. The model calculates the exposure index for its shoreline points as the geometric mean of all the variable strengths, like we can see in the formula. And we can see also an example of the rank applied for natural habitats. For example, mangroves, we applied the rank 1 for the very high protection of the coast. We calculated the exposure index for the entire coast of Mozambique, and the results show that the total number of points at which exposure index was calculated is 77,000 points, with a minimum score of 1 representing low exposure and thus a higher protection of the coast, and a maximum score of 4.6 representing a high value and thus low protection of the coast to flood events. The main output of the model were exported in QGIS software, and the model results were measured to obtain impact visualization at the level of both individual coastal provinces and at the level of the whole country. As we can see from the graph, the 33% of the Mozambique coast reported a low exposure index, while 58% reported a medium exposure index, and 8% reported an high exposure index. This 8% may seems like very low value, but in reality it means that more than 6,000 points of 77,000 points have an high risk. And considering that each point was calculated at a distance of 100 meters from each other, it means that more than 600 kilometers of coastline has a very high exposure index to erosion and storms. Looking in more detail at the statistics of various provinces, we can see that, first of all the provinces have a percentage of value classified as high of exposure index, and that in all the provinces the percentage values classified as medium is very high. And another thing that is evident is that continuing southward from Inhambane to Maputo City, the values classified as high increase in percentage. And since the model was calculated at a resolution of 100 meters, the most explanatory maps of those are those that were made at province level. In this case, it was also possible to include the distribution of mangroves as well as coral reef and seagrass. Here we see this explicative map of the exposure index with the presence of mangroves, coral reef, and seagrass on the left. However, since the model also takes human population into consideration when calculating the exposure index, I also developed maps showing the distribution of human population near the coast, as in this case again for Maputo City. Here we can see the high level of detail of the model that having set a resolution at 100 meters, the software calculated the model considering even around the perimeter of small islands, which are very frequent in the province of Cabo Delgado. So, Invest Coastal Vulnerability Model has proven to be an efficient tool in having a pragmatic visualization of Mozambique coast, allows in the identification of areas at high risk of flooding and erosion. By combining this result with mangroves distribution or time series data or mangroves extent, it's possible to use this tool to establish area of highest priorities for conservation and restoration activities. Also, working at the whole state level is a time expensive process if high resolution is to be preserved, as in this case, where the exposure index was calculated every 100 meters along the entire coastline. In addition, cartographic representation and simple pie charts are very effective tools to place on the table of decision makers. Every conservation and or restoration action has an high cost, so starting from a nationwide base or on where to focus efforts and available resources is a very important step to convince different stakeholders. So I'm done with that, and thank you everyone for your attention. And this is my email address. Please contact me if you have any question about work. And thank you again, and goodbye.